The Mystery of High-Energy Cosmic Rays. Presented by Science at NASA. Hold out your hand for 10 seconds. A dozen electrons and muons just zipped unfelt through your palm. The ghostly particles are what scientists call secondary cosmic rays, subatomic debris from collisions between molecules high in Earth's atmosphere and high-energy cosmic rays from outer space. This daily shower, which never stops, is a sign of violent events in deep space. It's believed the majority of cosmic rays come from supernova explosions. When massive stars explode, they blast most of their material into space. The expanding shock waves can break apart interstellar atoms and accelerate the debris to unimaginably high energies.
Magnetic fields have been a curiosity for thousands of years. And so, of course, we know now that magnetic fields are generated by what's called dynamo action, the convective motion of an electrically conducting fluid. Even though we can map the Earth's magnetic field with extraordinary accuracy with satellites in orbit about the Earth, the one thing we can't do is see clearly through all the crustal magnetization that is right beneath our feet. Jupiter is a gaseous planet, hydrogen, helium. There is no magnetized crust that obscures our view of the dynamo deep below. So the exciting part about the Jupiter mission is that we'll be able to image for the first time the magnetic field on the dynamo surface in a way that would never ever be possible on Earth. Jupiter is also the planet with the largest magnetic field. Its magnetosphere is huge. If you were to look up into the night sky, and if you could see the outline of its magnetosphere, which you can't, it would be about the size of the moon in the sky. It's a very, very large magnetosphere. In fact, in the Voyager program, we learned that the magnetic tail, the part of the magnetosphere that is drawn away from the sun, extends all the way out to the orbit of Saturn and in all likelihood beyond. It's a very large feature in our solar system. It's a pity we can't see it. JUNO's the fastest spacecraft ever to venture into the outer solar system. It's the first to orbit pole to pole about Jupiter, and it's the most heavily shielded spacecraft that we've ever launched. The mission is designed to basically wrap Jupiter in a dense net of observations, completely covering the sphere. So to do that, we need a polar orbit, one that passes over the North Pole, along a line of longitude, and over the South Pole. And we do this over the 37 orbits of the nominal mission, and by the time we're done, we've got orbits separated in longitude by about every 12 degrees. So we completely cover the sphere. A magnetometer is, it's best to think of it as a fancy compass. Unlike a compass that just records the direction of the magnetic field, our instrument tells you both what direction the field is in and what the magnitude is. And we can measure that very, very accurately to 100 parts per million. JUNO's magnetometer is another in a long line of magnetometers built here at Goddard Space Flight Center, following designs developed by Mario Acuna years ago. Our instrument is between 1 and 2 orders of magnitude more accurate than anything that's flown to Jupiter before.
To understand electricity, you really have to understand what atoms are made out of. So they consist of a nucleus that has a neutral charge and positively charged particles. And around that nucleus, you have electrons, negatively charged particles, that are orbiting around it. Now, if you are rubbing, for example, like when you're rubbing your hands, you are giving these electrons that are going around the nucleus of an atom energy to leave its orbit. You take him out of that structure and make them mobile. And it's really the flow of these electrons that produce electricity.
So the atmosphere is largely neutral. And so you need some energy somehow to break the electrons and away from the neutral atom or molecule. And the way the ionosphere is formed is largely through the extreme ultraviolet radiation coming from the sun. That provides the energy by which you can separate electrons from the atom, and they become free electrons. That atom now becomes positively charged, which is an ion, and that makes up the charged part of the ionosphere, largely from the solar extreme ultraviolet radiation. As we get deeper into the atmosphere, that radiation, it gets absorbed by the upper part of the atmosphere and doesn't reach the surface. You need more energetic particles to further ionize the atmosphere as you get closer to the surface. That's partly brought on by galactic cosmic rays. They have very high energies that can get through the atmosphere, and in that path have a lot of energy, collide with neutral particles and create ionization that way. There's also energetic particles from the magnetosphere that come in, and they also create collisions and create ions in the lower atmosphere. And then finally, at the surface, you have radioactive decay when one outcome is radon. And that radon will come up and emanate from the surface and create charged particles. So the distribution from the surface all the way to the edge of space is variable, but it's this distribution that is so challenging because there's chemistry and there's physical pathways and there's external sources and forces that make it very difficult for us to account for it all. But we know those ions constitute the conductivity of the atmosphere.
So I'm from Penn State University and Communications and Space Science Laboratory. In that lab for the last 10 years we have been very actively engaged in development of theoretical understanding of transient luminous events in the Earth's atmosphere. So we work on a variety of subjects related to lightning and lightning behavior, lightning physics, and of course in the context of global electric circuit modeling. We want to quantify how much lightning contributes to the global electric circuit, for example, in comparison with electrified thunderclouds and electrified clouds. There is a significant controversy in existing literature as to how much lightning contributes. So in some cases, some scientists actually claim 40% of the total current which is flowing in global electric circuit is contributed by lightning. So we want to actually understand and quantify actual amounts.
On climate, those are very complex questions. We first have to understand the basics, which is what we are doing, in order to see what other impacts it has. So our first goal is really to understand all the components of the global electric circuit, all the components of the electrical processes that are going on in the atmosphere, and then build on that.
Basically. So if you forget everything else I say tonight, the one thing to remember here is that Earth's atmosphere is always electrified. Normally, we just think about charge when there's thunderstorms and lightning around, but it's electrified all the time, and charge is continuously generated. And that's through a process called ionization. So positive and negative charge is created by ionization all the time. And in our atmosphere, there are two sources of ionization. The first is from galactic cosmic rays. So these are highly energetic particles from basically out of space, from outside our solar system. And they enter Earth's atmosphere from above. And as they do so, they create a cascade of charged particles right down to the surface. And because they come from outside our solar system, they're modulated by solar activity. So they respond to magnetic fields. The other source of ionization is radioactivity at the Earth's surface. So this is mostly from gamma radiation from the soil. And so this emits ions which can be transported upwards, but they're typically trapped in the boundary layer. So they're stuck in the lowest kilometer of the atmosphere. So this charge is being generated all the time. Looking at this. So how do these clouds become charged? Well, to do that, we have to think about some of these atmospheric electricity parameters a bit more. So we have to consider what's called conductivity. So conductivity is the ability of the air for a current to flow in the air. And it depends on this ionization from our cosmic rays and from our radioactivity. So these tiny little ions that are created in a cloud, they become attached to the droplets. And that means that the conductivity goes down when you have a cloud layer. So this is our cloud layer. We're going up through a cloud layer. So our conductivity decreases, is low in the cloud, and it increases when we get above the cloud. If we go to Ohm's law, which if you remember back to your school days, you probably did this in the form of V equals IR. It's basically the same equation, just written in a different way. And that says if you have a current, so in this case, JC, it's flowing through the cloud, and you have a conductivity or resistance, basically the same, the inverse, then if you have an electric field, then the conductivity and the electric field are inversely related if the current stays the same. So because we have a conductivity decrease, we must have an electric field increase in the cloud. And if we take another relatively simple law of electrostatics, so Poisson's equation, that says if you have a gradient in electric field, then you will create a charge, a space charge, rho. So you see that there's a gradient in the electric field on the bottom edge of the cloud and on the top edge of the cloud. So that means that we should get a charge, rho. And that's what we see here. So this is our charge density. So because of the direction of the field and the current flow, we should get negative charge at the base of the cloud and positive charge at the top. And if we manipulate these equations a little bit more, this charge depends on a few things. It depends on the conduction current, so our JC, which depends on the global circuit and therefore the thunderstorms. It depends on the conductivity, which depends on the ionization from the cosmic rays. It depends on the gradient of the conductivity, which is this bit here, which depends on the height of the cloud, but also the cloud droplet properties. So if we have a really sharp cloud edge, we should see more charge than if we have a woolly one, if you like. So that's what theory predicts. So our theory predicts that cloud edges are charged and that the charge should be transferred to the cloud droplets. So what does this charging of droplets do? Well, we'll discuss this in a bit more detail shortly, but basically it affects the microphysical interactions between aerosol particles and droplets. And collisions and coalescence, which is something that's particularly important in clouds, is affected by charge. So this means that things like the lifetime of the droplets, how long they last, and how they grow can be affected by charge. And many of you will know that it's these small-scale cloud microphysical processes that determine the large-scale properties of the cloud, such as the height of the cloud, its opacity, or how much its reflectivity, basically, how long the cloud lasts, and even the rainfall.
Ben Franklin began the study of lightning 260 years ago, but to this day, scientists still don't fully understand how it forms. Sure, the basics are known. It's like a zap of static electricity, except on a much, much larger scale. In stormy updrafts, raindrops and ice particles rub together. Some become positive and others become negative. Then they're pushed apart by wind within the storm cloud. As a result, the cloud ends up with areas of different charge. Lightning is the spark that jumps between these areas. These sparks can also fly between the negative areas of the storm cloud and the positive areas on the ground, say through a tree or a golf club. Simple, right? But there's a problem. The electric fields measured in thunderstorm clouds typically aren't big enough to trigger a spark. So what sets it off? Maybe cosmic rays. The idea goes like this. Cosmic rays, which constantly bombard the Earth, produce fast-moving, highly energetic electrons. These electrons collide with air molecules, which produce more speeding electrons, and so on. This process is called runaway breakdown and leads to an avalanche of energetic electrons through the air. These electrons forge a conductive path in the air, which triggers the discharge of lightning. Of course, the theory hasn't been proved, and there are other ideas for sparking mechanisms as well. It will take more work to fully solve the puzzle of how lightning forms. In any case, remember, the next time you get zapped pulling on a wool sweater, it just means you momentarily caught a little bolt of lightning. For Scientific American's Instant Egghead, I'm Philip Yam.